So welcome everyone to this first strength seminar series talk in this new year. And today we're very happy to have Luca Nutricati from Durham, and he's going to tell us about the running of gauge couplings in string theory. Please, Luca.
Hi, thanks. And of course, thanks to the organizers for giving me this opportunity. So I'll talk about the running of the gauge coupling in string theory. This work I've been doing with my supervisor, Steve Abel and Keith Venus. And hopefully it will appear soon on the archive. So let's start with a bit of motivation. Two important things about closed string theories. These theories are UV-IR mixing theories, which is a consequence of a profound and deep symmetry of these kind of theories, which is called modular invariance. And despite these, despite having these beautiful properties, they may have divergences, especially in the IR end of the theory, in the IR sector. So the questions here are basic of two natures. So the first of all, one may wonder, how do we treat these divergences without breaking modular invariance? And then one may wonder also if it's sensible to introduce a space-time energy scale and a renormalization procedure, which fully respects this UV-IR interplay, this UV-IR structure. So the outline of this talk will be the following. I will review some of the classical expression for the one loop corrected gauge couplings in string theory, and some basic things about modular invariance and this UV-IR mixing. We will see in this framework, in this in this kind of setup of one loop correct gauge couplings, how the divergences may appear and how to deal with these divergences. I will explain a bit how to regulate these divergences. I will focus on a modular invariant regulator, which has been recently used in a paper by Steve and Keith. And I'll focus later. I will talk about an example, a famous example, a famous class of computifications, and we will see how to use this kind of regulator in practice. So first of all, let's highlight some differences between strings and fields. First of all, in quantum field theories, in usual quantum field theories, if one wants to compute the one loop corrected gauge coupling, if the convention setting this convention in which the kinetic term of the gauge boson is precisely 1/g², one has to compute this diagram, which is precisely the propagator of one loop, and then extract the coefficients. This coefficient will be the correction to the gauge coupling. In string theory, instead of the one-dimensional bubble, a single, let's call it Schwinger parameter, we have a complex parameter, so a two-dimensional surface, which is, of course, in this case, a torus. And one has to compute the one loop amplitude, toroidal amplitude, and then one has to extract the coefficients 1/g² again. So instead of a one-dimensional surface, we actually have a two-dimensional surface, which is parameterized by the so-called Tech-Muller parameter or modular parameter tau. So in the first case, in quantum field theory, in usual quantum field theories, usually we have a finite amount of states which circulate in the loop. But instead of string theory, one has an infinite tower of Kaluza-kind state of Planckian mass that are circulating in the loop. So even though the correction is exponentially suppressed in the mass, because everything in the partition function goes like e to the minus tau 2m², the correction may be quite sizable, but because we have an infinite tower of course, these states. So as I said, the diagram is flattened. We have a torus instead of a bubble, and we have to integrate. So this is maybe another non-trivial difference. we have to integrate on all possible inequivalent tori. So this prescription to integrate on all inequivalent tori is precisely what leads to this the so-called fundamental domain. So the tau, this is the tau plane. So this tau 1 and tau 2 are the real part, the imaginary part of this complex parameter, and these each value of this complex parameters is parameterizing actually a two-dimensional, so a torus. So if we want to regulate, integrate on all possible inequivalent tori, we have to choose a fundamental domain. So every choices which every choices of this fundamental domain are valid. For example, for our conventions, I choose this gray zone here as our fundamental domain, but one can choose, for example, S or T or whatever. Every choice is perfectly fine and will lead to the same physics. So at the beginning of this talk, I said that these kind of theories are UV-IR mixing theories. So let's see why I said that. So let's start with this choice of fundamental domain, just this gray zone. And one may wonder whether we are excluding the UV. In particular, when tau 2 goes to infinity, this will correspond to the IR end of the theory, because everything is in the partition function is exponentially suppressed. Every massive state is exponentially suppressed, like e to the minus tau 2 m squared, and we are left only with the massless states. So this is the IR end of the theory. On the other hand, when tau 2 goes to 0, we are left only with the UV, because everything massless is suppressed, and we have only the UV. So one may wonder whether these choices of fundamental domain is neglecting the UV of the theory. The thing is that if, for example, if we choose this S as our fundamental domain, one again can wonder why we are including only the UV. The question is, the answer is the fact that the S symmetry, since the physics is the same in the F domain and in the S choice, the UV-IR mixing are actually folding UV with the IR. So both of these choices contains both IR and UV. So IR and UV are treated on the same footing in the theory. So the theory actually doesn't distinguish what is UV, what is IR. They are only the same thing. So having explained that, we can talk about the full one-loop correction to the gauge couplings in closed string theory. So this expression appeared in Kaplanowski in his seminal paper 1987 in a slightly different way, and we will see why in a couple of slides. So the expression of the corrected one-loop gauge couplings is, of course, an integral on the fundamental domain of an expression which contains a bunch of modular functions, which are Dedekind eta, Jacobi theta. And in particular, we can see how this expression split in two parts: the spacetime part, which is related to the four-dimensional theory, and then the internal part, which is parameterized. I parameterize with C, A, B, and depends on the compactification we may choose. We see also a bunch of insertions which will weight the state. For example, we have a Cartan charge and the Kac-Moody level at which the group factor is realized, and this is with K alpha. So the important thing, though, is the following. If we, let's say, compute these integrand for massless states, the massless states will give us some constant, which I call BA. This constant is precisely a supertrace on massless states, which are actually weighting the states with the helicity and the Cartan charge, but is precisely a constant. So what happens with the constant? So if we evaluate this integral only for massless states, we will have something like constant on tau 2. And when tau2 gets large, this integrand, the function we are integrating, goes like 1 over tau2, so which is log divergent. So the problem with that is the fact that the massless state in the full corrected gauge coupling gives the massless states give a log divergent contribution. And furthermore, we have some problem with modular invariance, because the contribution of the massless states is not modular invariant by itself. Because if we take this integral and then we multiply it and divide by tau2, we will have something which is modular invariant. This one can show very easily that is completely modular invariant. But this is this piece here, tau2 times a constant, is not modular invariant by itself. The consequence of this is the following. So this is the expression that precisely appeared in Kaplunowski in paper by Kaplunowski in 1987. Actually, this is the first thing is the full one loop corrected gauge coupling, but in order to make the integral finite, we have to somehow regulate it. And the way that Kaplunowski did that is simply a subtraction on the contribution of the massless states. So the problem with this subtraction is the fact that, yes, we are on the one end, we are computing the contribution to the one loop corrected gauge coupling, which is the contribution to the gauge coupling at one loop coming from the infinite tower of massive states, and so we are neglecting the massless one. But the problem is the fact that this divergent is actually this way of regulating the divergence breaks worldsheet modular invariance, because the first piece until this CAB is completely modular invariant, but this constant is not. So what we can do instead of subtracting, let's say, the pathological behavior of the integrand, we can do several things. The first one is the thing I just explained. So let's start with the integrand on the fundamental domain of some function f, which behaves like c tau2 when tau2 gets large. So in order to regulate this, we simply subtract the divergence. So it will break modular invariance again. We can introduce instead a cutoff in the fundamental domain. This has been done by Donzegir in 1981. And here we are actually introducing a cutoff in the fundamental domain. So we are integrating from the bottom part of the fundamental domain to some cutoff f. This is completely finite because everything is finite here. The function well behaved, and the fundamental domain is cut. But then we have to integrate from t up to infinity on these strips, and it is more subtle here. It is maybe trickier, but one can show that worldsheet modular invariance is broken again. So instead of doing this kind of prescription, what we can do is deform the integrand in a modular invariant way. So instead of subtracting things or introducing cutoff, we can deform the f in a modular invariant way. So we start from f, we go to f times g, where g is the regulator, and we ask that this g should be modular invariant. It must suppress any power law divergence for large tau2, and should leave the rest of the theory intact as much as possible. It, roughly speaking, is something like an Heaviside theta, a modular invariant Heaviside theta function, let's say. Okay, this is a possible choice of this regulator. For example, this g is a function which is completely modular invariant in tau. It depends on 3 parameters, of course: tau, which is the modular parameter of the torus, rho, and day. So let's forget about rho. Let's just put it to some number greater than 1. And A is actually can be related to an energy scale. So this regulator is based upon a regulator used by Kritzis and Kunnas in 1995, but it has been modified in a critical way. I already said that we can relate an energy scale to this parameter A with this parameter alpha prime that gives the right dimensions. And so this regulator respects the modular invariance that UV are mixing because it enjoys scale duality symmetry. So this regulator is invariant under this under the symmetry, and if we want to use that as a 4-dimensional regulator, we better make sure that this is respected. Okay, this is the profile of the regulator. Of course, I plot here as a function of only 2 parameters, tau2 and A. And we see when tau2 is greater than a certain threshold and depends on A, which is roughly 1 over A squared, the regulator starts to exponentially decay, exponentially crushing everything. So it will exponentially suppress any power law divergence when tau2 is large enough. Beyond this, it's larger when larger than this threshold 1 over A. And when tau2 is below this threshold, the theory is preserved. So the regulator is roughly 1, and the integral will be roughly the function we are integrating. We want to integrate. This is the profile of the regulator with different values of an A. That is exactly what I've already explained. Okay, let's see what happens in the famous case of a 6-dimensional n equals to 1 theory that goes down to a 4-dimensional n equals to 2 through a toroidal computification. Also, this is a famous result in the 1990 by Kaplunowski, by Dixon, Kaplunowski, and Lewis. So the threshold correction they computed is the following. So the main ingredient of this integral is this u22, and we see that the whole integral, it's beautifully computed by them. It will give a log of some theta function, eta functions. But we see that for massless states, so the massless state will come when these k are all equal to 0. This u22, is actually a constant. And again, thanks to this subtraction here, which is the contribution again of the massless state, they made the integral finite, they compute it, and capturing all the dependence of the threshold on the space-time moduli, so the moduli of the space-time torus. The problem with that, again, it will capture, of course, the whole dependence of the moduli, the space-time moduli, but on the other hand, we are actually spoiling modular invariant again, because this tau2, the second piece of the integral, which is the subtraction again, is not modular invariant. So what we can do is the following: instead of subtracting this in the contribution of the massless states, we deform the integral again, adding this regulator. So now everything is regulated and modular invariant. So the result we got is the following. So the full, again, the contribution of massless and massive state to the one loop gauge coupling is captured by this expression here. So the first, the interesting part is maybe one of the most interesting things is maybe that the fact that this expression contains the old result, so the DKL result, the result by Dixon, Kaplunowski, and Lewis. But again, some correction appear. In particular, there is this logarithmic, which is something that we expect because when we, I recall that when we take the a goes to 0 limit, the regulator is roughly 1. We are restoring the unregulated theory. So here in the limit when a goes to 0, something has to blow up. So, and this is precisely the hallmark of the divergent. Of the divergence, and then a bunch of correction which restore full sheet modular, worldsheet modular invariance, which can be expressed as the double sum on transformation in PSL to Z, which with some Carly K function, which in turn can be written as a double sum on Bessel function of the second kind. So this is a bit of a mess, but it contains all the required behavior in limits. And if one can approximate for some energy scale in A and gluing all these pieces together, we get something like this, this plot. This is the running of the gauge coupling. So this is 1 over G squared. Actually, it's not G squared, it's the inverse. So if we start from the d pi r, we say that we see that the dashed line correspond to the, of course, to the logarithmic blowing up, and the IR value is precisely the decayal one, so the log of the ethos. So if we increase a bit the energy scale, going from the d pi r, we at a certain point we hit the lightest state of the theory. And then it starts an EFT approximation, so an EFT regime. And the interesting thing here to stress is the fact that we are not applying, we are not introducing by hand the EFT approximation, so a log mu behavior. This kind of EFT approximation is coming out from our framework. So, and when we enter in, when we approach this UV, the most possible UV, so which is of course the string scale, one can show that it is actually a fixed point here. So the beta function is vanishing, and as soon as we go beyond this, the string scale, the theory must run backward in the same way. So the theory must repeat itself from this turnaround point with to the dual d pi r region. So this is again, this is not a UV, this is a dual IR. Okay. To conclude, we regulated the theory fully respecting modular invariance and UV-IR mixing properties, and we see how all these things emerge. We've seen how gauge couplings run in a particular class of computification in the DKL case, which is a K3 times T2. But the important things to stress here is the fact that this formalism can be applied in full generality to any model. So indeed, we use some methods we developed in this paper by Steve and Keith, and we work out the general case, and hopefully it will appear soon on the archive. And that's it. Thanks.
Okay, thank you, Luca, very much for this talk. So are there any questions? Or maybe while someone else comes in the question, maybe can you just show me your last slide again, on the conclusion. So you said for this Higgs mass computation, or in fact, you said you can apply it to any model. Can you just maybe briefly give like a overview about what this model is in this paper by Steve and Keith about Higgs mass?
Okay.
So what's the input sort of string theory construction that they're working in?
Yeah, it was actually model independent. The paper is about closed string theories, and they assume that the theory is already Higgsed, so they are already in the minimum of the potential, and then they actually constructed out how the theory will look like in this minimum. And this is actually model independent, so they use a formalism with supertraces and all this stuff about modular function, in particular ranking Selberg methods and so on. computing the second derivative of the potential, they get an expression which is in terms of supertraces of the mass. So this formalism can be applied, but it's not actually. It's something related to modular function and methods like Rankin-Selberg that you can apply it also in this kind of context of gauge coupling and stuff.
Okay.
So it's actually model independent.
Okay.
As soon
Yeah,
as,
that's a question.
as soon as you have, as long as you have modular invariance, you can use this kind of techniques.
Okay. Michael, go ahead.
Yeah, one very basic question. So I'm a bit confused. So these all Dixon, Kaplanowski, Lewis, these were all supersymmetric models, right? You had models with n equals 1 SUSY. Your discussion is now what I thought that Keith and Steve did something on the non-SUSY case. So which scenarios are you considering now? Do you have n equals 1 SUSY in 4 dimensions or not?
You can have whatever you want. I mean, it will.
But in fact, the question whether the Higgs mass runs, of course, crucially depends on whether you have SUSY or not, doesn't it? I mean, to which extent, how it runs, or.
Yeah, I mean, you can. Yes. So you can. So as I said, as long as you have modular invariances, it doesn't matter if you have SUSY or not. You can apply these. And also in the paper, we didn't assume any SUSY. So
sorry, but you proposed a modification to this Dixon-Kaplanowski-Lewis. Dixon-Kaplanowski-Lewis, as far as I remember, is n equals 1 SUSY in 4 dimensions. Now you propose a modification. You say that modification, you get always slightly modified Dixon-Kaplanowski-Lewis, regardless of whether you or not you have SUSY in 4 dimensions.
Yeah, exactly. Yeah, that's what I'm saying.
Okay. Okay, thank you.
Thanks.
Thanks. Okay. Are there any other questions? Okay, if not, then